Again, thank you very much for inviting me here. I come over here, you may find my presentation is less technical, more promotional. Or my colleague here, Lance Schadman, Dr. Lance Schadman, we are working on together. We try to promote and really try to get a project going related to the LG. What we give it a name, we call it environmental enhancing energy, E-square energy. And we'll introduce this. And also, I think this audience, and especially with the ISTC here, we have a lot of complementary aspects, especially the analytical. I hope that through these presentations, I will strengthen the relationships, the collaborations between my department and these institutions. So we have a project already ongoing that Dr. Schadman students working on the algae. I just heard that you have some algae growing in this building. So again, you may ask me more technical questions through this presentation, but I just give you a warning ahead. This is not much of a technical, or rather than it's more promotional. So it's environmental enhancing energy. We try to give a name, and we feel that is an appropriate title for talking in the Sustainable Technology Center. This is the energy issues, and just quick rundown of the energy. This is the 2004 data by BP. If you look at from the bottom, the purple lines is the consumption, and the blue lines is the production of these four major economies in the world: USA, China, Japan, and Germany. And right now, U.S. consumes 20 or 21 million barrels per day, and we only produce 7.5 million barrels per day, which is 57% rely on the import. And China actually changing quite a bit, and last year is already 7 million barrels. China is increasing the consumptions really fast with the economy. And Japan, Germany, they don't produce any. Everything has to be exported. So with that, there is increasingly talking about the national security on the energies, etc., etc. But just let's talk about the energy. And we also know that in the oil shale in United States, in the Green River basins around that Utah, Colorado, and Wyoming, we know that this can be already commercially produced, and that's by the Argonne National Labs. This we know the reserve there is anywhere between 1.5 to 1.8 trillion barrels of crude oil reserve. So this is the 3 times. This is roughly about the 300 years our oil reserve here. So it's encouraging, isn't it? And the tar sand, we know that the tar sand in the Athabasca regions in northern Alberta, and that is another proved reserve is another 1.7 trillion barrels, which, according to DOE, is another 3 years of crude oil reserve there. So, and it's already commercially produced. This is a $4 million Caterpillar truck that we can really produce in this way, extract it and separate it, etc. And so, not mentioning the coal. United States is rich in coal, and in coal we know this technologies for liquefaction. Liquefy the coals into the synthetic oil is already widely available, and since the 1920s. And that is anywhere, depends who estimated, anywhere 150 to 200 years of the oil reserve. So in that case, just energy alone may not be necessary that urgent problem. The real challenge is those fossil fuels not only have this energy, but also bring us the problems with the pollutions by the vehicles and by the refineries, and this is one of the sand oil refineries in Canada, and not mentioning all those coal power plants around the world. So the real challenge is twofold: energy, but also the carbon emissions. So on the other hand, economic development demands on energy, and yet energy consumption has historically really cannot live really with the environmental protections together harmoniously. These two seems always contradictory to each other. So that's the real challenge. Now, in past almost a decade or so, that we are looking voraciously for alternative energy, especially the bio energy aspect. And there are two major sources. One is the lignocellulose, which is on the left side here, and go through the different physical, chemical, or biological treatment so that we can get the liquid fuels, gasoline, diesels, or jet fuels. The other source is from algae. It's non-lignocellulose streams. And there are many paths and many approaches now to convert these different feedstocks into the hydrocarbons. So at this point, it becomes a general consensus among the scientific communities. There was some variations of these definitions: the first generation, second generation, and the third generation of the biofuels. First generation is grain and sugar-based ethanols. Very much is getting pretty hard during the Bush's administration, and pretty soon we know that it's going to be just a transient phenomena. The second generation now, in 2005, DOE finished a 10 years so-called billion-ton study, which in the United States we can effectively collect 1.3 billion tons of lignocellulose from crop residues and other woody stuff without adversely affect our soil conditions. And that is a great source for converting the lignocellulose feedstock into the liquid fuel. But primarily, again, it's ethanol kind of fuel. But since 2006, and we are starting looking into the third generation of the biofuel, because even with our billion-ton in the second generation, it's only estimated about 25% or so of national liquid fuel demand. So we need to looking beyond, especially coupled with the carbon emission issues. So the third generation is maybe the algae and the bio-waste. There is a great potentials in that regard. We know that all the energies, almost all the Earth, comes from sun. Okay, whether it's the protons, and whether it's fossil fuels, solar, hydro, geothermal, wind, and the biomass, of course, and not really nuclear. Actually, they get rid of the nuclear from there. But some argument is this: once we understand how the universe initiated, then we may have a different interpretations on this. Based on this, the widely accepted theories based on the biogenic hypothesis today is all the fossil fuels found on Earth, including the petroleum, coals, and the natural gas, are formed through a process of a kind of thermal chemical conversions. In particular, that with the algae and all other biomass matters form the crude oil, and the woody stuff form the cools, and the natural gas is from the combinations of this. So that's the biogenic hypothesis, and we also know in terms of the photosynthesis efficiencies, and of all these major bio-oil feedstocks, you see from here, from castors, sunflowers, safflowers, palm trees, and soybeans, coconuts, etc., and algae. That algae is by the far the most efficient photosynthetic feedstocks on Earth. And right now, the lab data shows we can get to 5 to 6% of the photosynthetic efficiencies. And yet the other biomass, including the Miscanthus and the sugar canes, probably below 2% of the efficiency. So there is a potential for that. Now, algae, then research, that has been started since the late of the 1970s. The DOE got this aquatic energy source studies. They pretty much pulled the plugs in the late of the 1990s. But over the past 30 or 40 years, there are plenty of the technologies already developed, whether it's economically viable or not. Existing technologies include mechanical extraction and the solvent extraction or supercritical fluid separations. But there are some limitations or bottlenecks related to the algae to oil conversions. That's including, I summarized it here, the three major bottlenecks. One is algae to oil require, so far, high oil content. Without the oil in the algae, it's hard to extract or separate. And the two is most of the processes now requires drying. You first need to dry the algae and then process it. And the drying algae itself is a very energy intensive and process. And thirdly, to produce the higher oil content algae, those algae species are usually very easily to be contaminated by other species. So those are the three limits the economic viability and for the algae to oil approach. So now some of you know in my labs since 1996, my group has been working on this. We call the TCC battery reactor, but it's very much a hydrothermal process. We successfully converted the swine manure into the oil. I bring, since most of you already finished the lunch, and I have brought two samples. And one is oil samples from manure, swine manure, and one from the algae. It's not manure anymore, it's oil, it's crude oil. If you want to take a look at that, we'll be able to do that. And with the swine manure, you can open it and look at the oil. One, the oil is still fluidable. So the swine manure is pretty much solid. It needs to be fluidable until 35 degrees Celsius. So we have a very high efficiency for the swine manure in the raw oil. So we'll be able to do that. So we actually send the oil samples to the NIST, National Institute of the Measurement Technology, the standard technologies, and it's branded as a so-called number 6 crude oil. I don't know what's number 6 specifically. It's a pretty low quality crude oil. It's a crude oil, not ethanol, not biodiesel, but crude oil. And we have some major analysis components of the carbon, hydrogen, and you may notice this oil is indeed very low quality because it have a high oxygen content. The heating values is pretty. It's also lower than the petroleum yet. Again, this is the research, early stage research, and but it's much higher than the ethanols. And this is the continuous reactor. Actually, my students now today, actually, they are running another set of tests using this continuous reactor. After our battery test, in this reactor, we can continue to pump in the manure. And now we are testing on the algae today. And then the other end, we can get the oil, crude oil. The capacity is about, one day we can produce 1 gallon of crude oil. And this is the pilot plant. One of my PhD students, after he graduated, he actually took off just scaled up the lab reactors and built this in Houston. And this is 40 barrels per day capacity. And right now, the company is building 160 barrels per day commercial plants this spring. So now, the reason I from the algae and then to the manures and then to the HTP, I want to make a point is that we also now focus on the algae. Our algae in one of the samples you see, the algae is so much nicer stuff than the swine manure. It smells less, of course, the cleaner looks like. But it's also very consistent. It's uniform materials. Swine manure is so complicated. I still don't know what exactly in it, and we still don't know what exactly we're converting it into. It's a crude oil, but that crude oil is very complicated. So I hope that someone in the audience can help me to analyze that upstream and the downstreams. So we now we are, but don't be afraid. It's not that yucky. It's once we convert it, it's just the crude oil. It's similar to the crude oil we get underneath the earth. This is a slide that show we did a series of studies for the algae, and we tried a specific kind of a species of the algae, microalgae in particular, and we tried the specific species, Corallina, Spirulina, and also some mixed cultures we collected from USD, the Urbana-Champaign Sanitary District, and we also mix up with the manures and with the different ratios. And we find that one thing, let's take the first column, for example. This purple shows the lipid content in the algae. With the existing technologies, get the oil from the algae, you have to have a higher oil content, right? Without this lipid content, then there is no oil extraction. But with our conversion, so we are converting it, not extracting it. So we are be able to, even with those no oil algae, we still be able to convert it into 35 to 40%. Actually, my lab showed today we're about to 45%, up to 45% in my lab. That samples is actually yield 45% of the oil from the spirulina. So the key things we don't need the higher oil content. Even with a very low oil content like this, it's less than 0.5%, we can still effectively convert it into oil. No, it's not just lipid. Lipid is still the oil, but what we convert is other things, even the carbohydrates and proteins, all these things. So that's, I think that's probably hold the promises that we can solve this first bottleneck with these algae things. Not necessarily we need the high lipid, because high lipid usually means low production, low yield. And second, because of this hydrothermal, we don't need to dry. This is we treat it as a sludge, 20% of solid, 80% of water, typically. So that's why we thought this is a hold a lot of. Here is the concept of environmental enhancing energy. We still, again, I'm promoting it. So we hope that develop a major programs with Dr. Scheidemann here. So our idea is to using this approach to hydrothermal process the bio-waste and the algae into the crude oil. And during the process, first we get this bio-waste, whatever it is, separated, and the solid into the crude oil. But the wastewater, which contain most of the nutrients still in it, and we can grow algae using the wastewater, and then grow more algae, and the algae feedback produce more oil. So in this process, we can keep the nutrients in the loop. Actually, in the lab, we showed that we can keep about 75 to 80% of the nutrients in this loop. We only extract hydrocarbons as the crude oil. And the output is we can clean our water, and we can reuse the water. So that's so during this process, we'll produce the energy or oil, but at the same time to protect our environment and keep the nutrient. Sometimes we call it a pollutant for the water sources in the loop. So that's our overall kind of a concept of the idea. So we dubbed it as the environmental enhancing energy. So that makes sense to us. That our E2 energy process will convert the bio-waste from animals, humans, and food processing into crude oil via the thermochemical conversion, and then produce algae using the wastewater from these streams. And then the algae will be fed back into the reactors to produce more crude oil. During this algae growth, then we can sequester the CO2, utilize the nutrient in the wastewater, so we can clean the water or reuse the wastewater. So therefore, we can improve our environment, so enhance our environmental quality. This further scientifically, we thought that maybe it makes sense because this thermochemical conversion process is mimicking really Mother Nature's process. Thinking about our biogenic hypothesis is most of our today's crude oil and coal is those bio-waste buried underneath the ground through million years of a process. It's a thermochemical, and we get today's petroleum and coal. And yet, this process we are doing in the lab, it's just we are engineering a process and reactors to be able to replicate the process in 10 to 40 minutes. We did that with the algae. We can do it in 10 minutes, and with the manures, it's a little bit tougher. We can do it in 40 minutes instead of a million years of time. And this thing I try to get more support and looking into the existing theories. And we didn't have some really detailed scientific theories. We don't know what really exactly going on during these conversion processes. But the conventional petroleum geochemistry and shows that our existing crude oils and the natural gases, if you look at the time, this is about 1 billion years, and with the temperatures underneath, this is about 300 degrees Celsius right here. And our all crude oil is formed under these conditions about a few hundred million years ago, under the conditions underneath the ground. So that is the envelopes, which is the conditions that form the crude oil. Okay, and our TCC now actually pretty nicely fall into this kind of a scheme, only that we have much more severe conditions, which is around 300 degrees in our reactors. But we'll be able to achieve in a minutes time scale. But they are still into this oil formation contours or boundaries. Now, if we can do some catalytic, which we try to do it, we have not really researched into much yet, and we potentially can improve this process or accelerate this process. Scientifically, we thought this makes more sense. Now, the big question is, hey, this sounds great. The big question is, can we produce enough of feedstock, which is algae, to really, that's being another bottleneck. When Dr. Schademan joined our department a few years ago, he said he's interested in algae. I myself is a doubt, because I didn't see much of algae myself, sometimes in the ditches or in the lakes, but did not really. And many people still challenge that how can we produce algae in a really, really large quantity and economic way. And so that is, I use this picture. This is in 2008, 1 month before the Olympic in Beijing. And this is my hometown. My hometown is, I used to, when I was a child, I swim in here. This is Pacific. I usually tell the friend, my American friend, where I'm from is, this is latitude 36. I told my friend, said, if you jump off from the Golden Gate Bridge in San Francisco, swim across the Pacific Street, and you reach here, which is my hometown. It's another side of the place. So it's a very nice resort, and 1 month before the Olympic, this is so-called Hu algae. The Chinese name is Hu algae. I don't know the English name yet. And see, the boom, the algae boom, is so severe the central government mobilized one division of soldiers plus 30,000 or so volunteers to clean this. You can see the magnitude. Every day the truck, just armies of trucks to take these things off. Second day is back to like this again. So they battled over about 3 weeks or so. And that's really struck me. Look, Mother Nature can really do something. And if we can engineer some system, we probably can produce. They would probably don't want to produce in these areas, but which means it's possible. So, and this kind of algae bloom is happening in many places in some polluted water sources, like some of the Great Lakes. This all happening in China. And those are the Great Lakes. This actual lake is the equivalent to our Michigan Lake here. So, and in U.S., we also have a similar problem, but not that severe. But these are indeed the so-called dead zone in the Mexico Gulf. And that, in terms of areas, is tremendous. It's about the equivalent to 20 million hectares of the areas. And actually, in DOE report, in the 98 report, it said if we can utilize efficiently these areas for algae productions, it can be equivalent of 2 billion tons per year for oil equivalent. We probably never achieve that, but this is the theoretical ceiling of the algae production and oil extraction potential. It's only potentials. So the question is, now we are not likely to use those valuable water resources just for algae productions. Now, again, back to our E2 energy, environmental enhancing energy paradigm. So we do have in the United States a lot of wastewater sources. Every town, every city have wastewater facilities, and all those animal buildings, dairy and hogs. Those, if we can use those wastewater, which is nutrient rich, and to produce algae, that's today's data. We have 54 billion cubic meters of wastewater collected already, and 200 million tons of manures in United States. If we all use this using today's theoretical lab data, we probably will never achieve the full 100%, but we are seeing the theoretical ceilings. When we see the ceilings, we can calculate the solar ceilings, wind power ceilings, or corn to ethanol ceilings. But this is another calculation. It can be used to produce algae and convert in equivalent to 6 billion tons of the crude oil. Again, we will never be able to achieve that, but the ceilings is very, very high. The potentials is very, very high. And there are lots of algae research already going on, and bioreactors, and we even have some on our campus. So this is our student sustainability committee. Dr. Schadman is the advisor to that. And this is some of the reactors. We come from some high-tech stuff to the low-tech. And this is actually Dr. Schadman's student doing this is in our yard, in our department. So again, back to my promotion mode. The environmental enhancing energies using especially algae, there is great potentials. The benefit is very obvious. It can safeguard our national security if we can utilize those wastewater resources. And of course, it can clean and reuse the wastewater, keep the nutrient or pollutant within the cycles. And also, it sequesters the carbon. And we use a lot of more carbon than only from the atmosphere. Then we maybe potentially can use the power plant or other CO2 sources. And it's less importantly that it's not competing with our food supplies. So it's really sounds too good to be true paradigm, but that's something we try to promote on these things. With that, I'm going to conclude my presentations and entertain more questions. And Dr. Sharma, you may, I just see a few slides at the end in order to get more technical questions, so you can help to answer on this. So the life, in terms of energy and the environment, I'm an optimist. This is my son. Life is so good. We don't need to worry too much, but we need to work hard on this. Thank you very much.
Yeah, I have two questions. Maybe one an easier one and then a harder one. Where does the phosphorus and nitrogen go?
Most of our phosphorus and the nitrogen, phosphorus primarily into the aqueous, the post-processed wastewater. We are above the 85% into the wastewater. So that's why we say, hey, we still keep those in the wastewater stream, so we can use it for algae growing.
But then the process will keep increasing. I mean, you need to
Yeah,
get rid of it.
true. Yeah, that's eventually it's not completely recycling. You have to still have input, which is the waste stream, and the output, which is hydrocarbons. But we still need to. It's a 15% need to be continuously removed instead of 100%. Nitrogen is there are two streams. One is in aqueous, and about 10%, still or close to 10% in the oil. The oil is not in the 10% in the oil. A small percentage in the oil, but most still in the aqueous stage, which is post water. But most of them, lots of them also into the solid stage. Depends on the feedstock. For example, swine manure. Algae is a really nice material, but for the swine manure ones, we have a lot of solid residues. At the end, about 15% of solid left, and then most of the minerals still remains in the solid, and the oils. In one table I showed you still contains oxygens, some of nitrogens.
So when that's burned out, turn to nitrogen oxide.
Yeah. And to answer your questions, see, when I see this is nice recycling, it's not 100%. And we are now in the lab with about 85% recycling. So the 15% we still need to have an outlet. So for the solid, we hope that maybe we can bag out for fertilizers or landscape people use or sell to the farms, because most of the minerals are still in it. But those are the things, again, lots of things we have not done yet. It's just the beginning of the research.
If I could follow that, you call this carbon dioxide sequestering and environmental enhancing. Now, if you wanted to be the contentious about that, one could say, at best, you are carbon neutral, at the very best, because you're going to be burning it all anyway. Right. And that's sort of in contrast to something like biochar, which can actually have carbon negative. So in terms of energy enhancing, some could argue that's a little bit misleading. And sequestering usually means saving it forever. Now, with coal, it's still just going to be carbon neutral because you're using fossil fuels, but you're sequestering hopefully forever. Here you're not. You're just using it, sucking it in, and then burning it again. So those are just some little nitpicking on your promotion.
Sometimes I could oversell these things. And now, that depends on the efficiency. When you see the carbon sequestering, maybe we should call it really carbon capturing. But it depends on the efficiency. You know, the other thing is, in this process, one thing I did not mention, when we convert using the HTP, our reactors, about 10% of the total mass is turned into the gas. Okay, we have solid stream, oil stream, and the aqueous stream, and also gaseous stream. Our gaseous stream is turned out 99% of the gas are CO2s. And this CO2, we are hoping in this whole scheme feed back into the algae growing. But again, the algae cannot take up 100% of this, maybe. Now, our idea is, hopefully, later on, efficiency improves. This can take up all the CO2s we produce in the process, and maybe take up some other CO2s, such as from power plant, or even has some atmospheric. Then in that case, if we can improve the efficiency, it's indeed, depends on how much of you're taking into, it's indeed enhancing. It's not just zero. But eventually, we don't want too much of a negative. Then we probably should enrich our carbon dioxide in the atmosphere. But we don't need to worry that yet. So you think, again, depends on the efficiency. Last, if I said something inaccurate, just jump in to correct me. Because that's a very good point. It's
capture more than carbon
sequestration.
The presumption is that the oil then displaces another fossil fuel. So if it displaces a fossil fuel, it's functionally, you get to carbon neutral very quickly. So if you were able to produce the 100% of the oil through this kind of means, you would have no net addition of CO2. And there would be some loss because the process is not 100% efficient. So you actually capture more carbon than you end up converting into an oil product. So it would be a little bit carbon negative in that case, just like any biofuel is in that sense.
I take you first.
Since your conversion process uses high temperature, high pressure, there is considerable energy input. What are you gaining once you're at?
Yeah, and this in the lab when we achieve the 1 to 3, one energy processing energy input and the energy in the oil content of 3, 1 to 3. Actually, in the pilot plant that they built, they used very good heat exchangers, counterflow heat exchangers. They be able to achieve 1 to 11, one energy. And actually, it's amazing that nowadays the heat exchanging technology is so mature. We can, at the pilot plant, they can get close to 90% of heat recovery from the process. So the differences of the input and output is very small. So therefore, it sounds like a very energy intensive, but if we recover all the heat and then basically maintaining all those heat in the system, and then we be able to achieve very high efficiency. In the pilot plant, they achieved 1 to 11. So, yeah.
Two quick questions. One is, how much area do you need to produce algae to run a small-scale refiner, let's say? And the other is the cycle. What is the production cycle between two harvests?
Okay, I have to run some calculation quickly. And you.
Urbana. If we did it based on a wastewater plant in Champaign-Urbana, collected all the wastewaters, and then grew algae on it, recycled all the nutrients from that, we'd need about a square mile of algae growing area. And we would produce about 10 times as much biomass of the algae as there was in the original incoming wastewater stream. So there's a certain wastewater solids content. We would produce about 10 times as much algae biomass in the recycling of the nutrients around in a loop.
In the winter?
And we assumed that you could grow it. We didn't talk about the time of year. This was 100% capture though of those nutrients. So yeah, you would potentially have limitations. Although, wastewater is processed year-round by microbes. So there are people that can work in not freezing temperature, but the wastewater comes in maybe 5 degrees C or something like that at the plant. So that would be the approximate approximate sizing that you'd be looking at.
And if you were co-located, you could use some of the waste heat to keep the algae ponds.
Absolutely.
And green water instead of blue water.
How long does it take to grow algae there? How many days, how many hours?
Well, algae can have a doubling time as little as 3 or 4 hours, and other species can have a doubling time that is as much as a month. The most high oil producing species grow very slowly. they're not that efficient at growing. But if you get the really efficient guys in the right conditions, they're not that dissimilar from bacteria. They have high doubling times, so they can turn over very, very quickly.
A lot of algae are associated with toxins. So if you're going to be growing algae in very large quantities, is there a possibility that you could be producing things that you don't want there?
Yeah, I mean, if you look at like the hypoxia zone in the Gulf of Mexico, there's airborne toxins that would come off the algae, and I think that is a potential problem for anything. If you look at the problem of something like hypoxia, a lot of the problems are subsequent to the algae growth. So the bacteria move in to eat the algae, and a lot of the hypoxia problem itself is related to that. So if we actually harvest it before you get beyond the death of the algae, you have a chance to avoid those toxins. But I think the airborne harmful algal blooms is an issue, and your only choice there is to try and do some species selection. Not all species are harmful algal blooms, but there certainly are some.
The toxin concerns or issues maybe to the benefit of our approach here, because we not necessarily just need a pure, for energy purpose, there is some toxins may not be a big concern versus the pharmaceutical uses. So
delineate between the air and the water, because if it's in the water, we'll destroy it with the hydrothermal process. But if it gets airborne, that would come off the process and be a problem.
Have you gotten to the point in your research where you're looking at the sensitivity of algae to CO2 levels?
Oh, that's part of the lab test right now. We do different exposures.
More CO2 is good as long as you don't depress the pH. So you can pump in a lot of CO2 that helps them to grow faster as long as it doesn't pull the pH down below 6 or something like that.
Given issues surrounding contamination or the wrong species getting in, is the direction of algae headed towards growing algae in containers or confined areas, or open air, very large?
Again, I'm going to direct the algae growing to less.
I think in the end, we don't know what will be the most economic. I mean, I come from something of a civil engineering background, so I tend to think large open tanks and basically take the infrastructure and the money that we're spending on wastewater processing and convert that over into algae generation, so that it would be large, outdoor, relatively uncontrolled growing conditions, letting whoever thrives thrive. But there are a lot of people going down the closed bioreactor range as well. They just tend to be more focused on higher value products. So they've got to grow something that they can use as a nutraceutical or some other higher value product to pay for their reactors.
In the winter, is your limiting factor going to be cold? In other words, if you had a pond, you could provide extra heat to it. Is there enough sunlight to keep the algae growing?
There's enough to keep them growing, but I think that the systems that you use on wastewater will end up being a combination of bacteria and algae. And so we're taking advantage. I mean, there's still a high organic load, and we want to use that to make biomass as well. Bacteria will work quite fine in the cold temperatures. This spirulina oil that he's passing around is actually a bacteria. It's a cyanobacteria. But I think we're thinking systems that combine algae and bacteria, not exclusively algae. And we've shown that we can convert the bacteria just as well as we can convert the algae, so we don't have to be so specific in terms of the technology.
Like your question ultimately would be what kind of future production systems will be viable. It's likely going to be a combination. Just look at our today's agricultural productions. There are open fields, large corn or soybean field, but we also have a lot of controlled environment, greenhouses or for the special. And it's really a matter of the economic capital cost versus the production or operational cost. And for this kind of system, for example, if the water near the city, maybe area is a problem, then we should have a more confined, space-intensive production system. In Arizona, in the desert, and we might as well just let it grow open. Last month, I visited back to China. One of the fellows running this algae growing in Mongolia. You know, Mongolia is lots of space, and they be able to produce some algae. So really, really cheap, but may not be very productive, but very, very cheap.
Question on the, you said about 10% of mass goes to gas, and then I'm guessing about 35 to 40% based on what the input stock
Right.
is converted to liquid.
Yeah.
And then the rest is solid.
Right.
And is that solid something that would be, it's like an organic solid mixed with ash?
It depends. I use these two examples. For swine manures, we have about 10 to 15% of a solid. When I say solid, 10 to 15% of the solid from our solid portion of the input. Okay, but for algae, we only have 3% of solid left, which means it's really good stuff. We only have 3% of solid left. After that, solid feedstocks, then we have 45% into the oil, about 35 or 35 or 40% into the aqueous. That's the part that we hope can manipulate, converting more into the oil rather than just the aqueous, and then 10% also into gases. The gases is mainly CO2.
Everything is exported off of the ag land and it's returned in some sort of synthetic fertilizer nowadays. And so, like, trying to close the loop on nutrient, is this something you'd be able to take the solids in return, say, to
That's something we need to do some analysis. But this is solid. We did some analysis before for the swine manure part. Most of that are the minerals, are the ash. It's not, it's inorganic. But I don't know how good are they, and they may be containing some toxins or not suitable for the land applications. But manure is a manure. We use it either for the land application all the time. It's just concentrated for some minerals and anyway. So how, again, there's a whole thing. You can imagine there are a whole area of the research and the question marks. I don't know yet.
Is the 1 to 3 energy ratio or 1 to 11 that you're saying, is that just for the crude oil and then you have to refine it?
Yeah.
Right, you have to refine it.
Yeah, but at what level can you do that? Can you do it on site?
I wish I could that in my continuous reactor, I actually leave a space for upgrading of the crude oil. But now I learned that our pilot plant, not our, but my student, and he just told me they have already upgraded their plant. They can upgrade on site. Before they just using it as a heating oil, run the generators, produce electricity, and now they upgraded to the gasoline and the diesel. So again, but I think that can be done. Crude oil is crude oil, even though it's a poor quality at this point yet. But upgrading the crude oil into gasoline or diesels is already exist. Technology exists. If we can produce a large quantity, somebody in the chemical or petroleum industry can happily to take it and refine it to the gasolines.
After the TCC process, how much solid do you left from the algae?
How many?
How much percent of solid?
Solid in algae. For this one, only 3% for this spirulina.
So it's all converted to
Yeah. 45 is oil, but the 40%, 45 at this point. But the others, it's liquefied. Now, that's another thing. So what's...
Go back to your overall E-squared energy diagram. So you're saying 45% goes into the oil. Oh, you went past it.
I passed this?
The NSF overview diagram. most of the rest of it is, like I said, liquefied and goes into the wastewater. So it's going to go out to the algae growing ponds. Right now we're assuming that's a loss, but in reality, I think most of that can be reharvested as bacteria. So I mean, it's going to be in the wastewater and go out there, and something's going to probably be able to grow it. But right now we're assuming that when we say 45% conversion, that's sort of the once through conversion. When it actually goes back out to the wastewater treatment area, I think there's a substantial chance that we'll recapture a lot of that 40, the additional 55% or so that's out there.
Right now, we hear this one conversion from algae to here. We converted 40% into this hydrocarbons. But the remaining aqueous is still back to the loop here. But the back loop, we are not capturing 100%, but at this point, about the 85%. So 85. So total, we can still substantially increasing the overall utilization efficiency. 20% of solid. Or we can manipulate, but just because of my lab of reactors, we designed that be able to handle that. If we could handle higher 25%, but then it's hard to pumping through because this continuous reactor is my tube is only a 3/8 inch diameter, so it's. But in industry settings, we may be able to handle much higher solid content because the pumping systems is more giving.
Do you see this technology scaling well in terms of, like, would it only be economically viable in large farms when you're using manure as the feedstock, or could you do it for smaller farms?
In 1996, when we first started this, then in 1999, we first time get the oil. We were really excited. So by that time, my initial thinking, our initial planning is every square mile, that's from an agricultural engineer's point of view, every square mile we should raise 1,000 pigs, consume the food, the feed locally, etc., and utilize some of the manures locally. But also have a furnace, home furnace size of reactor to convert the oil. That's our initial kind of visions. But these things, I think, is again from an economic point of view, especially from a chemical engineering point of view, skill matters, really matters. So the larger, that's why my chemical engineer colleagues always say, "Oh, these things never work." Our minimum size of a chemical or a petroleum refinery need to be such millions of barrels per day capacity in order to make it economical. So that's again is something that we need to looking into. But at this point, so if we treat it for like a typical normal size of the hog farm is about 10,000 hogs per year. And then it's reasonably we can set up a small reactor. Then the other factors. I calculated 10,000 hogs produce about 5,000 barrels of crude oil equivalent. This sounds a lot of oil, but who would bother or refinery bother of that 5,000 barrels to special treat or transport or this thing? It's quite a different story. So again, many of your questions, I don't have answers. It's just to raise all kind of new directions or new research topics. We do need to look into the economics of the scaling. But right now, the commercial plant, they are 160 barrels per day of capacities. So the industry did this, must be some potential benefit for that.
Compared to biogas, for example, what is the advantage or disadvantage? Why not go?
I think the most obvious advantage of this is the liquid oil. And it's not just a liquid fuel, which is easy to transport, to store, and high energy density, especially when we talk about the liquid fuel for jet fuel. So this is a potential, which ethanols and biodiesels It's a different type of fuel. That's the one thing. But I think the most important thing in the future is not just oil. Crude oil is not just for fuel. It's chemicals that provide us lots of other things. Our clothes, more than 90% of our daily life stuff is derived from this petroleum feedstock, right? So this thing, if it's a crude oil, then it provides us another renewable chemicals and the future feedstocks for many other things. So I think that's the future rely on not only just fuel in the future. Actually, in terms of economics, one of my students 2 years ago, because of our oil quality is so bad, we doubt ourselves, who is ever going to take this to upgrading into the gasoline? Then suddenly in 2008, in this July, when the oil price shooting up $147 per barrel, you guess what? The asphalt, the pavement asphalt, jumped to $720 per ton. And then suddenly, why didn't we just maybe you don't need much for upgrading and then pave the road or making roof materials? That could be still economical. It's so expensive, $700 per ton of the asphalt in 2008 July. So again, it's not just a fuel, but it's also potentially a new chemicals or materials